In this lecture, we're going to start the study of AC machines, alternating current machines. This is the first one we are going to study. It will be an induction machine. We're going to devote 2 lectures to induction machines. Today, you're going to see the basics of induction machines, how they work, what principle they operate. And then in the last lecture, we're going to address the modeling of induction machines in more detail, how we can estimate, for example, torque, speed, given an input voltage and a certain load. And then we'll build upon this in the upcoming lectures and see certain variations of AC machines, such as synchronous machines, single-phase motors, and so on. So by the end of this lecture, you should be able to understand the principle of working of induction machines. It's a basic. Today's lecture is relatively simple, but it will set the foundations for the next one. Model an induction machine, understand how it operates, and estimate the speed of an induction machine, giving a speed or a frequency of the input voltage and the characteristics of the machine itself. It's estimated that about 90% of motors used in industrial settings are induction motors. And well, this number is very high. So why is this number so high? Well, first of all, it has to do with the power they can deliver, and second, the way they are constructed. As you see later, they don't require the use of any permanent magnets. We simply have 2 coils, a set of coils in the stator, a set of coils in the rotor. They don't have brushes most of the time, which means that the construction of these machines would be a lot simpler to implement than an equivalent sized DC motor. A DC motor of this size would need giant permanent magnets inside. The cost will go up, and the maintenance of these systems would also be more important. Here, we simply have 2 sets of coils, one in the stator, one in the rotor, and we'll see how it works later. But the construction of these machines is relatively easier to do. The other fact is that the power they can deliver is typically much higher than an equivalent DC motor, which is very suitable for industrial applications. Here is another example. This is an induction motor that was built by General Electric, one of the biggest induction motors that has ever been constructed. I believe this one specifically here was built for a ship, for a generator, or for a motor in a ship. You can see the size of the rotor there. It's quite impressive. And you can go from one extreme to another. We have those giant motors and also have these small ones. If you open a blender or juice maker, whatever of these small appliances at home, such as washing machines, you will probably see an induction motor inside, or a variation of the induction motor, such as a single-phase induction motor. Why are they so widely used? Again, it has to do with their robustness and with the fact that they're relatively cheap to manufacture. So let's get started with the principle of operation. So today, let's focus on the principle of operation of these motors, and then in the last lecture, we are going to model that in more detail. The idea in a DC motor, in an induction motor, is that both the stator and the rotors will have sets of coils. Let's start with the stator. The stator that you see here has laminations of steel and a 3-phase winding, a 3-phase AC, each phase being shifted by 120 degrees. So we have these laminations of a ferromagnetic material that we stuck together, and then we put the coils around it. And you see here a set of coils that is put in the stator, and typically each phase will have a different set of coils, a certain amount of coils that are spaced symmetrically around the core. The input to these motors is always a 3-phase AC, again, each phase being shifted by 120 degrees. That's for the stator, or the fixed part. The rotor, the part that is inside that rotates, has a similar architecture. You see laminations of steel as well, and then you have coils that are built around these laminations. And as you see in the bottom example here, this is one way, so we would put coils like that, or this is another way where we can simply create a path for currents to develop in the rotor. Right? So both configurations exist. What is the idea here? The idea is that these coils that are now short-circuited, they are wound around the core, and the terminals of these coils are typically connected together. So that creates a path for current to develop. Same in this example here, we see bars of, let's say, copper that act as wires and create a path for a current to develop. So what happens when you put the rotor inside the stator? Well, if you take this stator and apply a AC voltage to it, and if we develop and if we arrange the coils in a particular way, there will be a magnetic field inside of this stator as a result of the AC excitation that will rotate at a given speed. The resulting magnetic field that comes as the result of all magnetomotive forces from all coils will have a resultant, and this resultant vector that represents the magnetic field will rotate at a given speed that depends on the input frequency. So we have an alternating magnetic field in the core. That's something that you can now use. If we put the rotor inside there, the rotor will see a changing magnetic field. What happens in the motor, in the rotor? Well, if the rotor is now a conductor that is in an alternating magnetic field, it will see a changing magnetic field. And this changing magnetic field, according to Faraday's law, will induce a current in the rotor windings. Hence the term induction motors, because the rotor is not powered, it's induced from or by the alternating magnetic flux in the stator. There is no physical connection between them. There is no external supply applied to the rotor. It sees a changing magnetic field. It's a conductor in that magnetic field. Now there is a back EMF generated in the coil, which creates a current. And this current that is now in a changing magnetic field will be subjected to a force according to Lenz's law. And this force then creates a torque. You see, the configuration, the idea is ingenious, it's simple. You just put a coil that is wound around the rotor and that is short-circuited in the terminals. And you put that in alternating magnetic field, it experiences an induction, hence the term induction motor. That induction creates a current. The current interacts with the changing magnetic field, experiences a force, and then that makes the rotor rotate. That's the basic principle of induction machines. And let's go talk about that in a bit more details. We saw that for Faraday's law, if we have a conductor that moves in a magnetic field or experiences a changing magnetic field, there will be a EMF induced in that conductor. And the magnitude and direction of that EMF is given by this cross product. The EMF depends on the speed of the conductor with respect to the magnetic field, depends on the magnitude of the magnetic field as well, and depends on the length of that conductor. And then you can use the right-hand rule to determine the interaction between them. If we now take this conductor and close the loop, this back EMF creates a current. And this current that develops in this conductor now is subjected to a force according to Lenz's law. And this force is given by the second equation we have here, I times L cross B. I is the magnitude of that current, L is the vector that gives the direction and the length of that of the current, and B is the magnetic flux density experienced by that conductor. So this creates a force, and this force now in the rotor will generate a torque, and the motor eventually conducts. So let's see here an example that I will make it more clear. So let's assume we have a wire that is there, it's in the rotor, and you have the stator windings here, three-phase. So we have three sets of coil A is connected like that, coil B connected, and coil C connected in series. And you have one wire in the rotor. And this wire is this black dot here. Let's assume that at this instant in time, the magnetic flux, the magnetic field rotates clockwise. So the speed of the conductor, and the conductor also rotates clockwise. Sorry, let me put it differently to avoid confusion. The conductor moves at a speed VB, and the magnetic flux at that instant in time points in that direction. If you now use the cross product V cross B to determine the induced EMF, the induced EMF will create a polarity like that, plus minus. We know that the current flows from the positive to the negative terminal, so the current would be moving inwards. If the conductor creates a current that moves inwards, now we can move to the second phase here and look in which direction that current will create a force. The current goes in the page. So if you now use the right-hand rule again, current goes in the page, then you have the magnetic flux pointing up, and the thumb now gives the direction of the force, which will make this wire move clockwise. Right? From these two equations, we can infer that if the conductor moves or is subjected to a changing magnetic field, it will experience a force in the direction of the rotating magnetic field. In the direction of the rotating magnetic field. So we can keep the wire fixed. We can put this magnetic field B, give this magnetic field B a speed VB. And if that is the case, then the conductor will experience a force in the same direction as the motion of the magnetic field. Okay, so first one here we have Faraday's law, describing the induction and the creation of the EMF. And in the second here, we have Lenz's law that now states that because you have a current developed in the system, the current will experience a force, the conductor will experience a force that when you merge these two analyses will be in the same direction as the rotating magnetic flux, magnetic field. Now our question is, how do we create an alternating magnetic field, and how we create a magnetic field that now rotates in the rotor or in the stator? And that's where we use the three-phase AC and a particular arrangement of the windings. The stator in this case is a two-pole stator, meaning that each phase, here's phase A, here's phase A prime. They're connected in series, and when we activate them, they create a magnetic flux, let's say, moving that way. Right. So you have two poles, north and south, for that specific coil. Then we have coil B here and here. With coil B is spaced with respect to coil A, or the axes here are spaced by 60 degrees. And then you have coil C and C prime. So the wires go in like that, they loop around and then go to coil C, and they close the loop like that. Okay, so the current circulates that way. And then all these three coils, they have a common neutral point, and now we have the same as the three-phase transformer we had before, three inputs, one for each phase. And we are now going to do, or we can use the delta configuration on the right here. And now we're going to apply a current to each of these coils, and the current will be shifted in a space electrically, by 120 degrees. Here we have the maximum current, cosine of omega t. Omega is the frequency, and then you have each subsequent voltage or current shifted by 120 degrees. That's for the stator. The rotor is the inner part here. The rotor simply has a path for a current to develop that will interact with the magnetic flux, either using the same configuration as the stator with laminations of steel or with a solid piece of conductor material. And then current would develop there as well. Now let's see what happens to the magnetic flux inside of this core. We have three phases. They are connected and they are equally spaced in the motor. And they are also equally shifted electrically by the same amount, which is 120 degrees. So what happens here? The top graph, we have all three currents, one for each coil, and you see they have the same magnitude, but these currents are shifted by 120 degrees. Let's take one point in time. Let's say time 0. Let's take time t0 here. At time t0, we have current A reaching its maximum, and we have current C and B reaching half of their maximum, but in the opposite direction. We can now see what happens in the rotor itself. We have coil A that it has its maximum value. Let's assume that a coil A has the along its axis has that value for the current. Coil B will have a negative value, so that it would go along B prime, but it's half of the first. And coil C is also negative and would have half of the other coil magnitude. We can now add these vectors together. We can do a vector sum here. So subtract them, we would end up with this resulting vector. We can move on to another point. Let's say this point now here. So this was A. Let's move to point B and do the same analysis. At point B, we have B and A with a certain amount. I think I made a mistake here. It should have been A. Should have been A, not A prime. So it would be pointing downwards. Right? It would be pointing downwards, and then A would be along A. It would be like this. And now we add them. We have the purple vector that is actually bigger. And let's move to B. So B, we have A and C. Sorry, A and B that are positive. So A and B positive will create, let's say, current like that. And we have C that is negative, and C is negative. So C would be pointing this way. And when you add everything up, we should have a vector now that it goes like that, the resulting vector. What do we notice here? We notice that as we shifted from these two positions, the direction of the resulting magnetic field created in the coils also shifted, has also shifted electrically. If we do this more precisely analytically, we'll see that the magnitude of these vectors that represent the EMF generated by the coil is constant. The magnitude is constant, but now the resulting vector changes direction. And as we now do a sweep here, this vector will start to rotate. And it rotates at a speed that depends on the frequency of the signals, depends on the number of coils we have. And the magnitude now depends on the magnitude of the current, but the magnitude is always constant. There's another little thing to consider here. This is just more a convention, more than anything else, is that these axes are the what we call the coil axis, but to represent the force that this coil would create on the rotor, we typically use a 90-degree shift because of the cross product. So this axis here would be the axis of that coil. The maximum EMF or the maximum force that this coil would produce would be 90 degrees out of phase with respect to that axis. So in the actual representations that we're going to see next, when you're dealing with coil A, we're going to assume that the resulting force created by coil A will be shifted by 90 degrees with respect to its own axis. But it's simply a convention. Right? It is easy to understand why, if you put a rotor like that, right, in the coil, in the current going that way, there would be zero torque. And remember the idea of the stepper motor. So by definition, if we are dealing with coil A, we are looking at a 90-degree angle. And now we can continue this analysis. Here are some examples of what we just did at some instance in time. We can look at a T1, T0, T3, T2, and so on, and see what happens with the resulting vector. And here is the same analysis we did before, just shifted by 90 degrees. What can you notice here? When you go from T0 to T1, electrically, we shifted, we moved on. If this is omega T, we moved on by 45 degrees. And the vector from T0 to T1 also moved on by 45 degrees. The magnitude of the vector has not changed, only the direction changes. So as we keep moving to the right, we see now this resulting vector rotating, in this particular example, counterclockwise. Right? And that's now an alternating magnetic field that will induce a current in the rotor windings. Okay. All right. So we can continue our analysis now. And if you create an axis gamma like that, we can evaluate the influence of each coil with respect along that axis. And to do that, we simply need to compare. Sorry, we simply need to compare the angle between the EMF or the force from each coil and the axis of interest, which in this case here between coil A and gamma would be theta. So the contribution of coil A along theta would be the number of turns of coil A times its current times cosine of theta, which is the angle between them. So this would be the MMF, the magnetomotive force of coil A along that axis. If you look at a coil B, it is the same, but now we add the shift of 120 degrees. Coil C, another shift of negative 120 degrees. And the resulting EMF along that axis is now a contribution of all three MMFs. As we saw before, this is just an analytical way to state the same thing. Now, as this magnetic flux rotates, it will rotate at a given speed, and it will depend on two things. It will depend on the frequency of the input current, and it will depend on the number of stator poles. By stator poles, I mean the number of coils in a given phase. Number of poles is number of coils, simply put, in a given phase. This phase A has two coils, and they are spaced by 180 degrees. It could have 4 coils spaced by 90 degrees, or so, and so on. And the same could apply to the other coils. So in this case here, the more coils we have for a given phase, the slower the magnetic flux will rotate, because it will, when you go from one coil to another, let's say this case here, it will simply, on a full revolution, it will do, for a full 2 pi phase shift, it will do a 2 pi revolution there. But if you have more coils, it will simply go from one coil to another, and as we add more coils, this angle that it will start to rotate decreases because you have more coils. It will be pulsating at different points in the rotor, but it will not completely do a revolution. We have locally a vector that it will move from one position to another. Right? So the more coils we add, the slower the magnetic flux will now rotate effectively in the core. And now the number of revolutions of this field will depend on the number of cycles of current. This is the frequency of the current, times the number of poles divided by 2, and times the number of revolutions of the magnetic field. All right, so number of revolutions of the magnetic field is basically the speed at which the magnetic field rotates. The speed in RPM is simply then, if you rearrange the equation above, we have the number of, or the speed in RPM, which is equal to, I just rearrange this as NS, just so for NS, here we have 2 times the frequency times 60, that's just to go from to RPM, divided by P, the number of poles. The number of poles. So what do we see? We see the frequency in hertz, times 60 gives the RPM, 2 over P, and the result is the speed of the magnetic flux is 120 times the frequency divided by the number of poles. This is what we call the synchronous speed. This is the speed that at which the magnetic flux inside the core revolves. It depends on the frequency and it depends on the number of poles. In this case here, we have a 2-pole machine because each coil has 2 coils. Each phase has 2 coils. Okay, and the more coils we add, then again we are splitting the rotor into smaller sections where the magnetic field revolves, and that will now make the magnetic field revolve at a lower speed. And again, this is what we call the synchronous speed, that it can be controlled based on the input frequency to the motor. All right, so now we know that we have an alternating magnetic field. It goes, I shouldn't say an alternating magnetic field. I should say a rotating magnetic field at a constant magnitude. And as it does that, as it rotates, the core experiences a change in magnetic field, and the core now creates its own induction, creates its own current. The current created in the core will affect the current created in the stator, because it's now a magnetic field itself that rotates in another magnetic field. Right? As the core develops a current, that current, or as the rotor develops a current, the current creates a magnetic field, and the coils that are all around the stator will also see a change in magnetic field. So the rotor can be seen as a magnet once magnetized. Let's call this a magnet like that. And this magnet is now rotating inside of the core, and will now affect the currents in the stator as well. So the rotor rotates at a given magnetic field at a given angle. We can, in this case here, with respect to phase A, would be B max times cosine of theta. Theta is the angle of rotation that depends on the speed. We know how to define the magnetic flux according to the magnetic flux density. Here it is, B times A. That's the definition of the magnetic flux. We can calculate the flux linkage as the maximum magnetic flux times the number of turns times cosine of omega t, which is simply here theta if it rotates at a speed omega. And I'll take the derivative of that to find the induced EMF. And the induced EMF as the rotor rotates inside of the core is simply the partial derivative of the flux linkage with respect to delta t, or respect to time, sorry. All right. So this is the flux linkage, and this is simply a vector that it gives the influence of this rotating magnet inside of the core with respect to a given axis. In this case, would be coil A. Right, and omega t is simply theta. That's the speed times time gives the position of the rotor. When you take the derivative of this, what do we get? When you take the derivative, we have cosine becomes sine, so the negative sign disappears, and you have omega showing up here. So let's see what we get in the output. With the output, we have sine of omega t. Well, that just gives the angle information or the projection along a given axis, and we have the maximum flux per pole. That makes sense. The higher the flux, the higher the induced EMF. The number of turns, that also makes sense. The higher the number of turns, the greater the induced EMF. And we have the speed, which also makes sense. The faster it rotates, the more EMF can be seen in coil A. That's for coil A, and for coils B and C, we can simply add 120 degrees. So this is to say that the induced EMF in the rotor will also have, the induced current in the rotor will also have an effect on the stator as it rotates. Right? It basically works as a transformer now. We have two sets of coils, and two sets of coils share a common magnetic flux that rotates. So, and that will now induce voltages in the rotor, voltages in the coil as well, in the stator as well. Okay, so let's continue this analysis. So this is the instantaneous induced voltage in coil A, which is what we just calculated there. These three constants, we can call these the maximum induced EMF, sine of omega t, and we can calculate the RMS voltage. So this is the maximum voltage omega times n times phi p. And if you want to move to the RMS, we simply divide that by square root of 2. So it would be omega n phi p over square root of 2. And if you want to now replace the frequency from radians per second to hertz, we simply have 2 pi f, where f is the frequency in radians per second. 2 pi divided by square root of 2 gives this magic number here, 4.4 times the frequency times n times phi p. Phi p is the maximum flux per pole. So this works fine for a coil with, for a stator with one pair of coils. If we have multiple coils, then there is a correction factor. This is determined experimentally, and this correction factor here is simply a constant Kw that typically varies between 0.85 and 95 to correct for the lost space between coils in the stator. Okay, so that's the RMS voltage induced in the coils. Now let's analyze two cases. Let's analyze the case where the rotor rotates and where the rotor is at standstill. So let's summarize what happened here. We have a rotor that has a changing magnetic field. We have a stator that has a path where a current can develop. The current developed in the rotor interacts with the rotating magnetic field. The rotor experiences a force, a torque, and then rotates. And look at the first statement here. The rotor rotates at a lower speed than that of the magnetic field. Why? The rotor rotates, we experience a torque, but it will rotate at a lower speed than that of the magnetic field. Any ideas why?
Because it has an internal mass.
Because it has an internal mass. Inertia, well, inertia could eventually, yes, during the transient, you're correct. During transient, that will play a role. It would have a mass and we have a friction as well to overcome. So during transient, that's fine. So, but it will also happen during steady state operation. And why is that? It would also happen during a steady state.
Is it because like we're generating the force on the wire, we're getting another current back EMF, it's producing a magnetic field. The outside's powered, but the inside rotor isn't. It's just gonna be going a bit below as its back EMF. Or like, I mean, as the stator kind of resists it?
The stator resists the back EMF. True, that's true. Yes, that's true. But that doesn't completely, we are getting there, but doesn't completely explain why it rotates at a lower speed. Because, you know, it could simply have a lower EMF than the stator, that's fine. But that doesn't really explain why it should rotate at a lower speed. But we are getting there, we are getting there. Any other guesses? Any other ideas?
Maybe eddy currents?
Maybe eddy currents. Maybe eddy currents. Eddy currents. Eddy currents, yes. So eddy currents would be a loss. Would simply be a loss in both the stator and the rotor. It would occur there. It wouldn't really explain why, but it does happen. Eddy current does happen. Well, let me give you a hint. The rotor needs to see a changing magnetic field, otherwise it doesn't create a current. Does that make sense? Right? If a conductor moves in the magnetic field, it needs to see a change in magnetic field to create a current.
Is it the same thing that we looked at last time with the DC motors, where I think as the rotor turns in the magnetic field, like when you change it, it doesn't actually go the full angled like displacement that the stator magnetic field goes, because the change in the magnetic field at the end is very small towards the end.
Okay, yes.
Something like
okay,
that.
I see. So you say that there is an axis of zero EMF. There's an
Something
axis
like
of
that.
zero EMF. Yeah. Okay. Yeah, that's true. That's true. Okay. Well, let's put it this way. If you take a wire and you approach a magnet to that wire, we'll see that as the magnet moves with respect to the wire, there is a current, right? Because the wire sees a changing magnetic field. If I stop the wire, what is the induced EMF? If I stop the wire and the magnetic and the magnet, if they're not moving with respect to each other, what is the induced EMF?
Zero.
Zero, because there is no changing magnetic field, right? If there was a changing magnetic, if there was an EMF, then well, there would be free energy. Just put a magnet close to a wire and you have energy. But we need a changing magnetic field. So if the rotor rotates at the same speed as the magnetic field, then the rotor sees no changing magnetic field, and the induced EMF is zero. The rotor now needs to lag behind the magnetic field in order to see it changing. It cannot rotate at the same speed, because if it does, then it sees no changing magnetic field. There is no EMF, there is no current, there is no torque. If you sit on the rotor and you look at the rotating magnetic field, we should see the magnetic field rotating is likely faster, and always we would see the distance to the magnetic field increasing. If you sit on the rotor, the magnetic field needs to pass by us. Otherwise, we would see no change in magnetic field. If we follow the magnetic field, d phi dt is zero. There's no change in magnetic field. So the only way for this change to happen is that the rotor rotates at a lower speed than that of the magnetic field. If it rotates at the same speed, there is no EMF induced in the rotor, there is no current, there is no force, there is no torque. Does that make sense?
I have a question.
Yeah.
If it's rotating at a slower speed, over time, wouldn't it lag behind? The distance that it's lagging behind increase over time?
The distance it lags behind, yes, the distance it lags behind will increase. Yeah.
Okay.
It will increase. Okay, so it needs to happen that way. And this discrepancy is what we call the slip factor. It will have two different speeds: the speed of the magnetic field itself, that we call NS, and the subscript S stands for synchronous speed. Synchronous speed, the speed that only depends on the applied current frequency and the number of poles. This is something you have control over. And then you have the rotary speed itself, that we are going to call N, which is slightly lower than the synchronous speed. We can now define the slip factor as the relative difference between these speeds: synchronous speed minus the rotary speed divided by the synchronous speed. And now the rotor is lagging behind. If you look at now this relative variation between these speeds, the relative speed between the rotor and the stator is Ns minus N. So the frequency of current induced in the rotor will have to be at that specific variation, at that specific, will depend on that specific variation, will not depend on the absolute value of the synchronous speed nor the rotary speed. The induced voltages will have a frequency that depends on the relative speed between them. So if you rearrange this equation here, we can calculate the frequency induced in the rotor as F equals to the speed times P divided by 120. What is the relative speed in the rotor? Well, the relative speed in the motor will be N S minus N. And that is what creates now the frequency in the rotor. And that's where this equation comes from. We are rearranging that equation, but now with respect to the relative speed between the rotor and the stator. We can replace ns minus n with, if you look here, just multiply both sides by ns. This becomes s times ns. And from the very top equation, we would have p over 120 times n times s times n. That is, sorry, this is exactly this equation here. So that's times s, right? This whole blue part is the frequency times s. So this is to say that the frequency induced in the rotor now is simply the slip factor times the frequency in the stator winding. And that makes perfect sense, right? Because again, the changing magnetic field from the rotor's perspective is the difference between its own speed and the changing magnetic field and the rotating magnetic field. So the current of voltages and the frequency of currents and voltages induced in the rotor will have to depend on that relative difference, on what is actually changing from the rotor's perspective. And hence now the current will have a different frequency in the rotor. Their current will be given by the slip factor times the frequency in the stator. The voltages will be the same we calculated before, but now the voltages in the rotor will have a different frequency. We'll have a frequency F1. Okay. Now let's analyze two possible operations to make this point a bit more clear. The first point is when the magnetic field does not move. So let's just think about it. If the let me rephrase that. The first operating point is where the rotor does not move. The rotor does not move. What is the frequency of induced voltages and currents in the rotor when it doesn't move? What is the frequency? If the frequency of the stator winding is F, what is the frequency of the rotor winding when the rotor doesn't move?
By doesn't move, do you mean like just before it starts moving?
It's maybe held at standstill. It's fixed. Yes, before it starts, assuming that it can't rotate. So what would be the frequency there?
It would be equal.
Would be equal, exactly. It would be the same frequency because now, since the rotor is at standstill, it sees the magnetic field rotating at the synchronous frequency. That's the relative speed difference, the speed between them. So at standstill, we'll have an induced EMF in the rotor because of the changing magnetic field, in the stator because of the changing magnetic field, and you have another induced EMF in the rotor that it now operates at the same frequency as the stator. The only difference between these two equations is the number of turns in each coil. One has N1, one has N2. They both experience the same revolving magnetic flux phi p. If you now isolate phi p here, you equate them, we can calculate the relative difference, the relative ratio between the voltages. This becomes a transformer. Is voltage 1 divided by voltage 2 equals to N1 divided by N2, which with this correction factors K1 and K2. Now let's assume that the rotor starts to rotate and it rotates at with a certain slip S. So now the induced voltage in the rotor and induced current in the rotor will now be subjected to this frequency that depends on the difference between these two speeds. The new frequency is now S times F. So from standstill, we had voltage E2. Now it starts to rotate. What happens? What changes? Well, the only thing that changes is the frequency. The frequency that was F now becomes F1, which is F times S. You see in this equation here that everything now, all these elements together except of S, this is the same as E2. That is the induced EMF, the induced voltage at standstill times S. So when the rotor is at rest, the induced EMF is E2. It operates at the stator frequency. When it now starts to rotate, its frequency changes to F times S. The induced EMF decreases to the steady state voltage times S. Will it increase or decrease? Will it increase or decrease?
Decrease?
Decrease? Yeah, it would decrease, right? Because now the relative speed has changed. The relative speed decreased. So if the relative speed decreased, the derivative of the magnetic flux will also decrease. And then E2 at the as it rotates is lower than when it's at standstill. Okay, so what can we conclude here? Two things also to keep in mind. At the start, there will be no back EMF to counteract the current applied to the stator. So when you start the motor, there will be a high current. The starting current in the induction motor will be high. Let me repeat that. The starting current in the DC motor will be high because there is no back EMF when it starts to counteract the input current. What else can we conclude? Because the rotor itself has a reactance, is an inductor, it has a reactance, the starting torque will be low because it takes time for a current to develop in the rotor. So the starting current is low. Sorry, the starting current is high, the starting current is high, the starting torque is low because it takes time because of the reactance of the rotor to develop a current and then create a torque. High start current, low starting torque. We'll see later how we can compensate or fix that issue in the second lecture. One last thing to consider, now I have three operating modes possible. Let's say we take an induction machine, we connect that to a DC machine. The DC machine can operate as a motor that will make the induction machine turn. So we could use the induction machine as a generator, for example. We have three operating cases. The first one is when the motor rotates at a lower speed than the synchronous speed. This would be the motor mode, right? The rotor rotates at a lower speed than the synchronous speed. That's the rotor mode. That's the motor mode. If the rotor rotates at a faster speed than the synchronous speed, then it's that actually the rotor is the one creating a change in magnetic field, and the system operates as a generator. It runs faster than the voltage induced in the stator. It's just the other way around, right? And let's assume that it has an external power that does that. And the third operating mode is the braking mode, where now one rotates in one direction, the other one rotates in the other direction because they are now rotating opposite directions. The torque between them will make the rotor slow down, and that would be a braking mode. So first mode, the slip factor was going to be between 0 and 1, 0 and 1, because the rotor rotates at a lower speed than the synchronous speed. The second case we have, sorry, this is the slip factor S, my bad. Slip factor will be between 0 and 1. The second case we have the slip factor being greater than 1 because now we are rotating at a faster speed. And the third example would have a opposite effect where the slip factor is less than 1. Okay. All right. So that's the last consideration. In a motor, the slip factor will always be between 0 and 1. Okay, so that's the principle of operation of synchronous machines. And later in the next lecture, we are going to see how we can expand this to create a to model the starting torque and the starting current. All right, this will basically be some sort of transformer. That's the only difference. Are there any questions about the working principle of induction motors? Isn't this an very interesting architecture? All you need is two coils. You don't even need a permanent magnet. You don't even need to power the rotor. There's no power given to the motor. It takes power, external power. It takes power from a rotating magnetic field. It's just simple and ingenious. Any questions? No? No questions?
Would you be able to just very quickly jump back to slide 17 for a moment?
Yeah.
If you could just quickly summarize it again, like it doesn't have to be super in-depth, just a reminder again, because I just kind of was trying to write down what you were saying once we got to the end of it, and I just wasn't able to, and I feel like I missed maybe a few key points.
Yeah, so
Thank you.
I think two things to consider. The first one is the standstill operation. When the rotor does not rotate, it sees a change in magnetic field that rotates at the synchronous speed. We'll have an induced voltage E1 and E2 in the stator and the rotor, respectively. Each has a specific number of turns, but each shares the same magnetic flux phi p. If you isolate phi p and combine these two equations in the same way we did for a transformer before, we can find now the ratio between I1 and I2, and that will depend on the ratio of the coil turns. In standstill, the frequency of the rotor is the frequency of the current in the rotor is the synchronous frequency. It's the same as the stator because it's at standstill. As it starts to rotate, it will now, the relative difference between its speed and the speed in the changing magnetic flux will decrease and becomes now the synchronous speed minus the rotor speed itself. The induced voltage and current in the rotor will now depend on the slip factor. So the frequency that was F now becomes F1, which is F times S, the slip factor times the synchronous speed. And if you rearrange this equation, we see that this becomes E2 times S. The voltage during operation as the motor runs is the standstill voltage times the slip factor S. That's the main idea here. Okay, and it makes sense because as the rotor starts to rotate, you will see a smaller variations in the magnetic field. The speed of the magnetic field relative to the rotor decreases, right? So if it does that, then the EMF needs to decrease as well.
Thank you.
All right, so let's do an exercise. Let's start with exercise 75. Let's do it on the PowerPoint here to save some time. So we have a 3-phase, 4-pole, 400 volts, 60 hertz induction motor that delivers rated output power at a slip of 0.05. Determine the synchronous and the rotor speed, the frequency of the rotor current. What is the synchronous speed? So we have a 3-phase, 4-pole, what else? 60 hertz motor, and operates at a slip factor of 0.05. What is the synchronous speed? Synchronous speed is 120 times the frequency divided by the number of poles, sorry, number of poles, which is 120 times 60 divided by 4. This is 1800 RPM. 1800 RPM. That's the synchronous speed. That's the speed at which the magnetic flux revolves inside of the rotor. Second question is, what is the rotor speed? This is the synchronous speed. Right? What is the rotor speed? How you
Can we
calculate
use
the rotor
slip
speed?
factor equation?
Exactly. So now we go with the slip factor. S equals to ns minus n divided by ns. We have everything here. We have the slip factor 0.05 times synchronous speed times synchronous speed minus the synchronous speed. This is equals to negative n, and n is, can someone calculate this? 1700, 630 something. Can someone calculate this? I'll calculate this on my phone. $1710 RPM. Okay, that's the frequency, that's the speed, the actual speed that the rotor rotates at. It's slightly lower than the stator frequency. What else you have here? The frequency of the rotor current. What is the frequency of the rotor current? Is the frequency of the stator current times the slip factor. So that is 1800, sorry, that is 60 hertz times 0.05, which is 3 hertz. It gives you a better idea of what is happening in the rotor. See, the frequency is only 3 hertz because that has to do with the relative speed between the rotor and the stator. That relative speed is 90 RPM. If you sit on the rotor, you will see the magnetic flux rotating at a 90 RPM, not at 1800. And because you are rotating at 1710 RPM. So the induced EMF will have a frequency of 3 hertz. The induced current will have a frequency of 3 hertz as well. Okay, very simple. Last lecture, we're going to complicate this as likely. Any other questions here?
Question?
Yep.
Is the difference always 90 or it's just for this example?
Well, it depends on the slip factor, right? If you change the load, the slip factor might change. Right? This, if you put more resistance, it will maybe lag behind more, or it depends really on the operating condition. So this not always, this is just for this particular example. If you change the number of poles, this will also change. If you change the input frequency, it will also change. Any questions? Any other questions? No? All right, so let's do exercise 76 then. We have a 3-phase, 60 hertz, 4-pole rotor that has 230 volts between the slip rings at standstill. This is to say, if you measure the voltages at the rotor at standstill, that is 230 volts. The rotor is connected to a DC motor whose speed can be changed. Determine the magnitude and frequency of the voltage between the slip rings, or the rotor voltage, when the induction machine is driven at the following speeds. And then here we have 5 different operating conditions. The first one being, it is 1620 RPM in the same direction as the rotating magnetic field, 1620 in the opposite direction to the rotating magnetic field, and 1800 at the same direction as the rotating magnetic field. So let's do this one. So here you have the question. We have 3-phase, 60 hertz, 4-pole, and the standstill voltage. That's something we can add here, because it says that we have 230 volts at the slip rings at standstill. This is what it called before E2S. The rotor at standstill, that is 230 volts. Okay, so let's now calculate the magnitude of the frequency, the magnitude and frequency of the voltage between the slip rings when induction machine is driven at these speeds. So what do we need now to determine that? What is the first thing we need? What do you need to determine the voltage when the rotor rotates? We need the slip factor. We need the slip factor, and to calculate the slip factor, what do we need?
Synchronous speed.
The current speed, the synchronous speed. What is the synchronous speed? Synchronous speed, because this is fixed at a 60 hertz for pole, that is going to be 120 times F divided by P. That is 120 times 60 divided by 4, which is again 1800 RPM. That's the synchronous speed. Now we can answer question A. What is question A saying? We are now rotating, the rotor rotates at a 1620 RPM in the same direction as the rotating magnetic field. So we can calculate the slip factor as synchronous speed minus rotor speed divided by the synchronous speed, which is 1800 minus the rotor speed given in question A is 1620 divided by 1800. And this is 0.1. That's the slip factor. It has no unit. Now we can calculate the magnitude and frequency of the voltage between the slip rings when induction machine rotates. It rotates at this slip factor. So what is the frequency in the rotor? Is the frequency in the stator times S, which is 60 times 0.1, 6 hertz. What is the voltage as the rotor rotates? Is the voltage at standstill times S, which is 230 times 0.1, which is 23 volts. All right. The rotor at standstill experiences this when it rotates at this specified speed. It drops to 23. That makes perfect sense, because if you sit on the rotor now, the rotor rotates at a the magnetic flux rotates at a lower speed than when the rotor was at standstill. Okay. Any questions here? Any questions? No, it's all good, right? It's just plugging numbers. Let's do B now. B says 1620, so same speed as before, but now in the opposite direction to that of the rotating field. So what changes? What changes? In A, the rotor was lagging behind the magnetic field. Now in B, because we connected this to a DC motor, it actually it goes in the opposite direction to that of the magnetic field. So what changes? How do we adjust these equations to calculate the new induced voltage and frequency?
Is it the slip factor that changes because of the opposing speed?
Correct, exactly. It's this slip factor, because now we are seeing the magnetic fields going in the rotor and the magnetic field going in opposite directions. So now the slip factor becomes 1800 minus the speed, which is now in the opposite direction, so negative 1620. There's a negative sign there, divided by 1800. And this is now 1.9, which gives a frequency of 60 times S, 60 times 1.9 is 100 and 44 hertz, and it gives a induced EMF at running condition as E2 times S, that is 230 times 1.9, and that is 437 volts. 437 volts. Okay, because now they operate in opposite direction, the relative speed has increased. So it is understandable that these two values would also increase. Any questions here?
I have a question.
Yeah.
Because the slip factor is more than 1, could you say that this became a generator?
It becomes a generator, yeah.
Yeah.
It becomes a generator. Okay, let's do C. Now we have 1800 RPM in the same direction as the rotating magnetic field. 1800 RPM in the same direction of the magnetic field. What is the induced current or is the induced EMF in the rotor?
0.
0. Very good. What is the frequency in the rotor? Also 0. Why is that? Because now the rotor, the magnetic field rotates at 1800 RPM. The rotor follows it at the same speed. The rotor sees the magnetic field, sees no variation of the magnetic field, no induced current. So both voltages and frequency are 0. Okay. Any questions? Any questions here?
Sorry, could you explain again why it's 0?
Okay. So let's assume that you have here the magnetic field rotating at 1800 RPM. The rotor also rotates at 1800 RPM. The slip factor is NS minus N divided by NS, which is 1800 minus 1800 divided by 1800. This is 0. The slip factor is 0. They both rotate at the same speed. If you sit on the rotor and you look at the magnetic field, you will see the magnetic field at standstill, even though you are rotating at 1800 RPM. The coils here see no change in magnetic field because they rotate in synchrony. They rotate at the same speed. The coils have a constant magnetic field applied to them. In a constant magnetic field, there is no induced current. There is no induced EMF. As they rotate at the same speed, there's no change in magnetic field. If they rotate at the same speed, or if they are both at rest, it's the same. The magnetic field from the rotor's perspective doesn't change. And if that is the case, there is no induced EMF. Hence, this is 0, that's 0.
If it was the same speed but different directions, and there would be a slip factor, right?
Yes, if they are rotating, which I believe is question D, if they rotate in opposite directions, then they need to go back here. And now this becomes 1800. Right? Negative 1800, and then the slip factor will be 2. Right? And then there will be a induced EMF of 460, and the frequency would be 120 volts, hertz. Any other questions?
I just got a quick question. So if we were starting, say, from rest, we would be applying power to the stator, and we would be causing this to rotate, and it would only achieve a speed a little bit less than what the stator's field is rotating at. But to get to 1800 and furthermore above that, it means spinning the rotor, like you said, using a DC source or a machine or something.
An external power source.
Yeah. because before it acts as a generator. But if it's at 1800, we have to do that too, because it's only going to get to 1800 by being spun, right?
Yes, it will only get by 1800. It will always, as a motor, you always run lower than the synchronous speed. It can never do this. And if it does that for whatever reason, the motor produces no torque.
Gotcha. And it's just because we're spinning the rotor at that speed, and there's just no. Okay. Thanks. Appreciate it.
That's it for today, folks. I have office hours starting at 10. I believe there's still one spot available if you have any questions. Otherwise, wish you a good weekend. I'll see you again on Tuesday for another lecture on induction motors. I'll see you then.